Hey everyone, we're getting a new topic today. That topic is electromagnetic waves. So for this one, it's kind of a continuation of our previous unit, which was mechanical waves. So we're using a lot of the same equations, a lot of the same ideas, some of the same concepts, wavelength, frequency, and so on. But we're going to apply them to this other special type of wave, which gets its whole unit, because it's kind of an interesting thing. So what are electromagnetic waves? What are this thing that we're really covering here? Sort of the simplest answer would be electromagnetic waves are light. Like everything that you see, all the different colors are electromagnetic waves. But it also comprises, light itself is a small part of the electromagnetic spectrum. So there's a bunch of different types of electromagnetic waves. You should have covered this at some point in your science career. I think Earth Science, this is part of your curriculum. Where you talked about all of these different things. Gamma rays, X-rays, ultraviolet, visible light, which are all the different colors that you can see, infrared, microwaves, which is exactly what you're thinking it is, radio waves, and at some point you should have sort of covered this idea. All electromagnetic waves are the same thing. It's just that if they have different frequencies, they have different sort of properties and different energies. So we can see things in roughly this frequency range, this times 10 to the 14th hertz frequency range, which is times 10 to the 14th times per second, or 100 million millions of times a wave goes back and forth per second. Some of these with higher energies and higher frequencies are like your gamma rays and X-rays. So X-rays are, again, when you go to the doctor and get an X-ray, that's what that is. Gamma rays, you shouldn't really see too much. They'll either give you cancer or turn you into the Incredible Hulk, one of those two things. And then on the lower end of the spectrum, we have radio waves, which are like things that are used to send your Wi-Fi signals or your, radio transmissions and stuff like that. But what actually are these things, these electromagnetic waves? The answer to that is not simple, so I just kind of wrote it out for you. They are made up of a magnetic field oscillating, which just means going back and forth, one way, an electric field oscillating perpendicular to that. So it's an electric field and a magnetic field, an electromagnetic wave, that's where it comes from. This is a picture of one that's not moving. It's a little easier to kind of get an idea of if we look at sort of something like this. So on the top you have a mechanical wave, and you can see why we did that first. It's just a little bit simpler. It's just a transverse wave, it goes up and down. Cool. And electromagnetic waves is just like a whole different sort of thing. It's an electric field that goes up and down, and then a magnetic field that wiggles like side to side or perpendicular to that as it moves forwards. So it's not like particles that vibrate. Like it's not water moving up and down. It's fields, which are kind of just like a more abstract, harder to grasp kind of thing. So basically what you have here is an electric field that goes up and down or oscillates and changes, and that creates a magnetic field. The magnetic field creates an electric field, so these two things like create each other as they go. And the result is you have a wave that sort of like creates or sustains itself. This is an electromagnetic wave. So what it is these two fields vibrating perpendicular to one another. Kind of a weird idea, but that's what it actually is. They are examples of transverse waves. We know that because notice the word perpendicular comes out of this whole thing. And that is something that you need to know, is that electromagnetic waves are examples of transverse waves. Transverse waves. So remember from the previous unit we did the longitudinal versus transverse. All of these different types of waves are going to be transverse waves. And electromagnetic waves have some really, really interesting things going on. Starting with the medium. All mechanical waves require a medium. Like ocean waves need water, or else you couldn't have them. Sound waves need air. Electromagnetic waves are totally different. This is kind of cool. They do not require a medium, so not required. That says not required. You can easily see that it says that. Oh, man, let's just get rid of this. Sorry. Alright, so I just kind of wrote it all out. So, medium is not required, which means that it can travel through nothing, or like a vacuum. A nice way to think about it is that sunlight reaches us from the sun, right? Which means it travels across outer space. And outer space is a vacuum. There's nothing there. So it can move through this sort of empty space. If it couldn't, then sunlight wouldn't reach us, and it would just be a very different world. So a medium is not required. It can travel through a medium, like light can travel through air or glass or water. They're all see-through, right? Light can move through it. So it's not required, but it can move through a medium in some instances. Electromagnetic wave speed. Here's an important one that you need to remember. All electromagnetic waves travel at the same speed. They all have the same speed. What is that speed? Well, it's the speed of light. Why do they all travel the speed of light? Because it is light. All of these electromagnetic waves are just, it's light. So they all travel at the same speed. If it's high energy, low energy, high frequency, long wavelength, whatever it might be, they all have the same speed. And that speed is a constant, which means it's in your reference tables. Front page, towards the top, and you have this right here, speed of light in a vacuum, 3 times 10 to the 8th meters per second. Since it's this sort of special speed, since it's a constant, we give it its own little value here, c. So every time you see c in an equation, it represents, yes, the speed, but very specifically the speed of light in a vacuum, 3 times 10 to the 8th meters per second. So they all travel at the same speed. Can't say that enough times. I'm going to bring it up a lot more times before this video is over. And lastly, energy. Some waves have more energy than others, and that's determined by the frequency. The energy of an electromagnetic wave is directly related to the frequency. High frequency means high energy. High frequency means high energy. So if we look at our electromagnetic waves chart, which is in the reference tables, I should point that out. This page right here, the second page, titled the electromagnetic spectrum, and all of your different types of waves are here. We've got them listed by wavelength up top, and then frequency on the bottom. Notice that these high frequencies, 10 to the 20, 10 to the 21st, are all of the smallest wavelengths, because to reach you more frequently, they have to be tightly packed. Here, we've got our low frequencies and our long wavelengths. Like 10 to the 3rd is 1,000 meters, which is almost a full mile long between successive crests of a wave. Out of these, the high energy ones are up here, the high frequency ones. High frequency, high energy. These are your gamma rays, your X-rays. They have so much energy they can go right through most things. Like X-rays can go through like flesh or tissue, but they can't go through bones because they're denser. They don't have that much energy. Gamma rays can pass through most things, which is why you have to wear like shielding, like when you get in order to stop X-rays, if you're around like a nuclear reactor or something like that. Then our low energy waves that are a little safer to be around are like, again, like your Wi-Fi signal and stuff like that. Those are your radio waves. Obviously, they're not super, super dangerous to you because then all of our electronics would hurt us. That wouldn't be good. So anyway, high frequency, high energy, that's the thing. So, all of that in mind, we can try a couple of these questions here. I'm going to do the first one, then I'd like you to try the next two sort of on your own. Number 1, what is the wavelength of a radio wave traveling through outer space with a frequency of 5 times 10 to the 4 hertz? Okay, thinking about what we know here. I think we know F is 5 times 10 to the 4th hertz. Cool, so that's the thing we know. We're solving for the wavelength, which is, again, we're trying to find it. And it seems like that's all we know. But we do know that all electromagnetic waves, which includes radio, you can tell because, if we go to our spectrum, radio waves. All of these waves have the same speed. We give it a special symbol, c, and it's 3 times 10 to the 8th meters per second. And if you got through that mechanical waves quest, you might have noticed that there was one equation that showed up an awful lot. It was, in our wave section, v equals f lambda. So this equation is going to keep popping back up for us in this unit as well, because it applies to all waves. So, v equals f lambda. Computer's mad at me today. Okay, we know that v is 3 times 10 to the 8th meters per second. And again, we know that because it's the same for all of these waves. Equals, the frequency I gave you is 5 times 10 to the 4th hertz. Okay, a little bit of algebra here, and I got a wavelength of, whoops, v equals f times lambda. I should include that here. This is getting a little cluttered. Okay, a little bit of quick algebra. You have to divide the frequency to the other side, and I got 6,000 meters. So this would be like a radio wave. It's got a long wavelength, relatively low energy. Alright, I want you to try numbers 2 and 3 on your own. So close the video, give them a shot, and I'm going to go over them in a second. Number 2. Beam of light has a wavelength of 4.5 times 10 to the negative 7 meter in a vacuum. What is its frequency? Alright, so again, we've got a wavelength here, because I told you that's a wavelength. We want the frequency, that's f, and right away there is an equation with f and lambda in it. V equals f lambda. And again, it seems like we don't have the information to do this, but we know the speed of light. It's a constant. It's 3 times 10 to the 8th meters per second. Equals, okay, now we're solving for f, but we know the wavelength. That says 4.5 times 10 to the negative 7 meters. Okay, solve for this one, and you do get a really big number. Light goes back and forth very quickly. So fast that we can't see light wiggle back and forth. We, interpret it as a color. I got 6.67 times 10 to the 14 hertz. Cool. 3. Describe 2 ways in which electromagnetic waves are different from sound waves. Okay, there's a lot of different things you could have written here. I'm just going to throw a couple up. You might have actually gotten more than what I'm going to put up. So for starters, light is faster. So that's a good one. Remember, the speed of sound from the previous unit was 331 meters per second. This is 3 times 10 to the 8th, or 30 million meters per second. So light's definitely faster. Light, I'm just going to say it because I can't seem to write these. Light does not require a medium, but sound does because it's mechanical. Light is transverse. Sound is longitudinal, so that would be a good answer. Yeah, so those would all be good answers. Cool, let's go. So we've got our spectrum, and again, all of these different things that you see written here, gamma, X-rays, UV, infrared, micro, these are all the same thing. They're all that electric field that goes back and forth, and then the magnetic field that goes back and forth with it. But having more frequency, or more energy, gives you some sort of unique properties for each of them. And it means that we can use them for different things. Like radio waves we can use to send signals. Microwaves we can use to, well, cook things. Infrared is sort of like a heat energy, is essentially what it is. Visible light is useful because we can use it to see. Ultraviolet is what comes from the sun. It's got a little higher frequency and a little more energy. It can be sort of damaging to your skin cells, but we can also use it to clean things, to kill bacteria, because again it's higher energy, a little more dangerous. X-rays are useful because they can pass through skin and stuff like that, but not through bone, which is how you can sort of create an image, like something like this. If you send an X-ray into someone's arm, this is my arm from a couple of years ago, see on the sides, like these X-rays can pass right through, but for the bone part, the X-ray, it cannot pass through. So like denser things, like the bone or maybe this metal right here, the X-rays can't pass through them. So they're kind of useful. Since they have more energy, we can use them to see through some things. And then gamma rays, which are sort of our more dangerous nuclear energy type things. So they're very high frequency. You probably don't see these every day. Okay. Now, what you need to be able to do is tell me what type of wave different waves are. That was poorly phrased. So what I mean by that is this. You have to be able to take a piece of information like this. This is the frequency of a wave. And you could reasonably ask to tell me what the wavelength of that wave is, the type of wave it is, meaning is it gamma, UV, radio, and so on, and tell me how fast it moves in a vacuum. We're going to do the first one together, and then I want you to try the rest on your own. So for starters, 5 times 10 to the 5th hertz, I'm looking at down here this frequency. Okay, so I'm going to do the type of wave first, just because you don't have to do any math for that. It'll be good. The type of wave, alright, 5 times 10 to the 5th. So what we're going to do is we're going to look for times 10 to the 5th somewhere here, which I think is right here. And it looks like that is a radio wave. So for your type of wave, I'm just looking for you to write radio. And that's it, that's good. Speed in a vacuum I'll do next, because it's actually the easiest one here. All of these waves travel at the same speed. It's kind of, well, it's not a trick question, but it's kind of a trick question. It's 3 times 10 to the 8th meters per second. They all travel at the same speed. All of these electromagnetic waves, all of them. I'm trying to make a point out of that. Which brings us to the wavelength. Unfortunately, we do have to do some math for that. But it's the same math that we just did. I'm going to do, I'll show my work over here. V equals F lambda. I'm going to run out of room, but that's okay. So, we know that V for all of these things, I think I filled it in over here actually, is 3, oh no, what did I just do? Times 10 to the 8th meters per second equals, the frequency is 5 times 10 to the 5th. And then we're solving for the wavelength. When you do that, I think you get a value of, I got 600 meters. If it looks familiar, it's very similar. I think it's off by 1 decimal spot from question number 1 that we did before. Okay, pause the video and try the rest of these. I'm actually going to just kind of fill in the answers and skip to that, and then go over how you were supposed to do each one of them. Alright, hopefully you gave these all a shot. So I just kind of wrote my answers. I really can't apologize enough about the handwriting here. So, to solve for the frequency or wavelength, it was just V equals F lambda over and over and over again. So you got to be able to use that equation. It's going to come up quite a bit. So hopefully you got my numbers. If you had trouble with it, just try plugging in one more time. If you really have trouble, stop by my office hours, Monday, Wednesday, Friday, 11 to 12. So that's how I got all these wavelength / frequency values. The type of wave you just kind of look up. So like here, times 10 to the 16 hertz, times 10 to the 16 is about here. So I said that's ultraviolet. Some of them there's an overlap here. It's like a spectrum. It's kind of not clearly defined. So if you put X-ray, I'd probably give it to you because they kind of overlap. They're in a similar region. So here, like times 10 to the 13. Okay, you just look it up here. Times 10 to the 13. That is infrared. Or IR. So that's how I looked all of these up. For here, this times 10 to the 14, that does fall into this visible category, but if you wrote infrared, I would take it. That would be fine. Alright, and last up, speed in a vacuum. I know it's like redundant to make you do the same thing over and over again, but I wanted to make a point out of this. They all travel the same speed in a vacuum. Okay? Which brings us to visible light, the last thing that we're going to cover today. Visible light is kind of interesting. So, when you think of all the different types of light, like everything you can see, all the colors, like everything you've ever observed visually is visible light. So you would think that that's like most of what's around us, because it's what you can see. Turns out that is not even close to correct. Out of this whole electromagnetic spectrum, see this little sliver right here? That's everything you can see or ever have seen. Those are all the electromagnetic waves that you can see. It's such a small amount of this electromagnetic spectrum that to even fit it on the reference tables, I had to sort of like expand it into this larger thing. Everything in this range is, again, all of your visible lights, and the different frequencies create different colors. So let's get that in our notes here. So you can detect different frequencies by seeing different colors. Different frequencies equal different colors. So some of the higher frequency colors that you see are like violet, blue, and those would be towards the higher end. So those are high frequency, high energy light. Lower frequencies is sort of like your reds and your oranges. If you're looking really carefully, you may notice that this is your Roy G. Biv here, like the colors of the rainbow: red, orange, yellow, green, blue. When you do the Roy G. Biv, there's an indigo in here, and then you have violet. So it's just kind of in the backwards order, Vibgyor, I guess, which is not as catchy. So these are all your colors of the rainbow. The reason that indigo was thrown in there, it's not like, doesn't really have to be there, is Isaac Newton's the one who figured out that light is composed of all these different colors, and he was fairly superstitious. He liked that it would be like 7, like there would be 7 colors, like lucky number type of thing. So that's why he threw an indigo, even though like you really don't need it in there. So these are all of our different colors, and you can tell that the violet blues are your higher frequency colors, because if you look down here, it's like 7.69, 6.59. These are the higher numbers for frequency. Down here we've got our lower numbers. So anything with a higher frequency than roughly 7.69, those are like more than violet, so they are ultraviolet, and you cannot see those. They're just outside of like what our human eyes are able to detect. So again, everything that you see is part of this visible light. The reason that we see that is it's because that's the part of the electromagnetic spectrum that's sort of the most intense here on Earth. So like here we've got a graph of all the different parts of the electromagnetic spectrum. It's kind of in the reverse order of your reference tables. But visible light is this little spectrum right here, and see how like the graph is the highest there? That means that that's where the light is the most intense. So this is just what our sun gives off to us, and it's why our eyes are adapted to that. If our sun gave off, let's say, light that was like maybe higher frequency, like let's say our sun gave off lots of X-rays, then maybe we would have all developed X-ray vision instead, and we could just like see through everything, which would be really cool, but also confusing, because things like glass might be like wouldn't appear the same way. We'd like crash into it and stuff like that. So anyway, kind of neat. So what you have to be able to do is take some information like this and tell me how fast this is going to be, what its frequency, and what color it is. We'll do 5 together. You'll try 6 on your own, and that'll be, I think, good for today. Alright, so we've got an electromagnetic wave with a frequency of 632 nm, which stands for nanometers. We'll worry about that in a second. For speed, you should answer this right away. 3 times 10 to the 8th meters per second. They all have the same speed. I really like asking that question, so you'll see it a lot. What is the frequency? Okay, now I'm hoping that this sounds a little familiar at this point as well. We have an equation that we can use for this. E equals F lambda. Electromagnetic waves are light, so they travel at the speed of light. 3 times 10 to the 8th meters per second. Equals, alright, we're solving for F. Now this 632 nm, m stands for meters, but it's this n that we got to figure out. You'll see this this n a lot in this topic, because that's roughly the wavelength range of visible light. So that nm, that prefix, we know what to do with that because it's on the reference tables, front page, bottom left. N stands for nano, which is times 10 to the negative 9. You'll probably get to memorize it because again it'll show up quite a bit. So what I'm going to do is 632 times 10 to the negative 9 meters. That is not proper scientific notation. I do want to mention that. But your calculator will pick up on that if you type it in this form. So, you can kind of just go with that. Okay, divide across, and I got a frequency of, 4.75 times 10 to the 14 hertz. That's the frequency. So if you were looking at this, if this light hit your eye from like an object, that would be a certain color you'd interpret it as. What color would it be? Well, let's take a look at a reference table to figure out what color it is. 4.75 times 10 to the 14. That's the number we're looking for. So 4.75, again, 4.75. You look down here, and we got to figure out which of these color ranges that fits into. So 4.75 is, I've got it here in this red section, and the reason I have it is 4.75 times 10 to the 14. See how that fits nicely in between 3.84 and 4.82? So this color would be red. Now, as far as like where it falls into the spectrum, the closer it is to this 82, the more orangey red it is, as opposed to like further this way, where it'll just appear as like just regular red. So this is kind of a spectrum, and if you like approach this boundary between the colors, that's where you end up with like a blend of the two colors. But for us, this falls into the red range, so that's our answer, red. Pause the video, do 6 on your own. I'll go over in a second, but give it a shot. Alright, I hope you paused the video and tried it. It's almost an exact replica of the previous question, so probably went alright. I did v equals f lambda. Again, v is 3 times 10 to the 8th. It is always that value for electromagnetic waves. We're solving for f, and we know the wavelength is, we're not plugging in 500, because it's not 500 meters, it's 500 nanometers. So we're plugging in 500 times 10 to the negative 9. Okay, when you do that, you get an answer of, I got 6 times 10 to the 14. As the frequency. We can tell that's a good answer because I start asking what color it is, and all of the colors are times 10 to the 14, so this seems good. But, so let's figure out what color it is. 6 times 10 to the 14, we go here. Okay, 6 times 10 to the 14 is bigger than 5.03, it's bigger than 5.2. I think it's less than the 6.10 though. Like if you put 6 times 10 to the 14, I think it would fall nicely into this green range. So that's the color that you would see. You would see like some form of green. Okay, so we did a couple things. The most important ones are electromagnetic waves have a couple sort of unique properties here. They all travel at the same speed, 3 times 10 to the 8th meters per second. They do not require a medium, so they can travel through nothing, like the vacuum of space they can move through. And the energy is directly related to frequency, high frequency, high energy. We also just got familiar with this diagram, being able to use it to figure out, like, if you have a wavelength of 200 meters, what type of wave that would be. So as long as you can read this chart and you remember these things from the beginning, then you're in good shape for today's lesson.